Hello there. I hope you're doing well wherever you're watching me from. So this is Mwalimu Ndolo or Tisha Ndolo. I want us to go through a paper that was done recently. That is Cambridge Physics, variant 4.2 extended. So this is a recent paper. I want to take you through as I'm aware that you're now preparing to do the exams for these coming May, June exams. So doing a paper like this will be good for your revision. So get some coffee or water and some notebook, calculator to confirm my calculation also, so that we can be on the same page. Once again, if you are new here, please subscribe. And also, if you cannot subscribe, then ensure that you share this with someone that can able to benefit from it. Thank you, and let's start. So whenever you have a paper, always confirm that the variant that is there is what you are doing. And then you are not seated there for core or extended, but now today we are doing extended. You can register for the core paper or extended. So it's always good to confirm, even though it is the work of invigilator also to guide you through that, but it is a good thing. Under the instructions here, there are always obvious one that you can able to to look into. But then the most important one is this. This is something that is really confusing learners. That the value of G is 9.8, that is meters per second squared, or 9.8 Newton per kilogram. So sometimes we get confused. We are still using the value of G as 10 from the old syllabus. So please be careful, or always refer, just in case you are doubting, always refer. That information is always given on the first page. The marks out of 80. So let's start. So question number one, as you can able to see in this figure, it is a speed time graph for the first 5 minutes of a bus journey. Okay, so describe the motion between, so describe the motion between the time when time is 0.9 to time is equal to 2.9. So 0.9, that is from here to 2.9, that is here. So that is the part that is a straight. We can able to see here that as time is changing, there is no change in speed. There is no change in speed. So therefore, that is a constant or uniform speed. But then when you're answering your questions, please, you choose one to use. You don't say or. So you choose one. If you decide to use constant, then that is okay. If you decide to use uniform, then that is okay. So you just choose one. I'll just be giving you options of what we can able to use here. So please, you can't be denied a mark if you write, let's say, no acceleration or zero acceleration. Why? Because when you say zero acceleration or no acceleration, it means two things. Zero acceleration means that the body is moving at a constant speed, or the body is at rest. That is why we have to be very specific for this particular question here. So that is a constant or uniform speed. Then 2.9 to 3.5. So 2.9 from here to 3.5, that is here. So 2.9 to 3.5. As you can able to see, the speed is decreasing actually from that value. This is, so if here is 7.5, okay. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 small boxes represent 2.5. That means one small box represents 0.2, 0.25. So that means at this particular point, this is 9.5, 9.5, yeah. So the speed is decreasing from 9.5 meters per second to 0 meters per second. So again, this is, and because the gradient is constant, so the body is decelerating, but then if we just put that the body is decelerating, we have to describe exactly, because if the part of the graph was like this also show that there's a deceleration. So we have to be very specific for this one here. And we have to mention this is a uniform deceleration. Forgive my handwriting, but we'll keep on working the best way we can. I am between 3.5 to 4.5, 3.5 to 4.5, that is down here. So you can able to see clearly that along the x-axis or the time axis, we have the value of speed is 0. So this is a confirmation that the body is at rest or stationary. So you can say stationary or you can say at rest. Again, if you say here that there's a zero acceleration has two meanings, as just we have mentioned. So you may not be given a mark for those particulars, so it has to be specific. But B, another bus travels at a speed of 8.9 meters per second. The brakes apply a constant force, and the bus stops in a distance of 23 meters. This bus has a mass of 18,000 kilograms. Calculate the kinetic energy of the bus before the brakes are applied. So from here, we all know, or you need to remember, you need to know that kinetic energy is given by a half mv squared. So that will be a half times mass, that is 18,000, times the speed. So before the brakes were applied, it was moving at 8.9 meters per second. So we use 8.9 meters per second, and then we square. So I'll use my calculator. So that is 0.5 and a half times 18,000 times 8.9 squared. That gives me 71,2890. If I look at the values that I've used here, they are into two significant figures. So I am allowed to have my answer 71. Then 1, 2, 3, that is 0,000 joules. Or you can give your answer into significant figure. I mean, into standard form, that will be 7.1 times 10 power. So this is 1, 2, 3, 4, 5 power 5 joules. So either way, please do not come here and write this and this like forward, and then you write here 7.1 times 10 power 5. I've seen that with some of the students before. Please don't do that. If you decide to use the standard form, please do that, because if you miss something, if let's say this is power, it's supposed to be power 5, and then you end up writing power 4, then you put here stroke. A stroke means that either this is right or this is right. The moment you do that, you will lose both the marks. So please, let us not try to make such mistakes. We really want to get full marks so that we can able to get an A star, a strong one. Calculate the force applied to stop the bus. So remember, for bus to stop, there must be work done. And that work done is equal to the energy that was transferred or that was being used, which is kinetic energy, So that means that the kinetic energy is equal to work done, and work done is given by force times distance. All right, so our value from here, move it here, okay. So our value from, so we have 710,000 joules should be equal to force times distance, that is force. The distance you can able to refer, the distance is 23 meters, that is 23. So therefore F is equal to 710,000 divided by 23. So 710,000 divided by 23. I'm getting 30,869 into two significant figures. That would be 31,000 joules. 31,000 joules. Correct. So that means you have already scored 8 marks if we are correct. I didn't get marking scheme, so Just in case we make any mistake along the way, you can always comment in the section, or if you have a new method, feel free to share with us also. Define impulse. Impulse is from here, from this formula here. Force is given by change in momentum times time. If you multiply both sides by t, you get that Ft is equal to change in momentum. So this product of force and time is the impulse, which can also be defined in terms of change in momentum. So impulse can be defined as change in momentum. So change in momentum. So if you decide to use change in momentum, that is okay. Remember, please, you've just seen change in momentum per unit time. This is the rate of change in momentum, which is equal to force, not impulse. So some people may forget and then add something here like rate of change in momentum. Rate of change in momentum is force. Or you can define it in terms of a product of force. So that is the force times, so force times the time. So this is the force of impact times the time of impact. Whenever there is an impulse, that means there's a time, there was a collision, something, so there is a change in momentum. Part B, figure 2.1 shows a rocket and its exhaust gases. Okay, so our understanding is that as the gas is burning, is being released downwards, the rocket gains an upthrust that is acting in the opposite direction to make it move forward. So the exhaust gases are emitted from the rocket with a velocity of 1400 meters per second and at a rate of 2800 kilogram per second. Show that the force exerted on the rocket by the exhaust gases is 3900 kilonewtons. State the equation which you will use. So I'm seeing here we have a mass. So in 1 second, we have a mass of 2800 kilograms. That means we have time. So time is 1 second. And then we have mass, which is 2800. We are given speed, which is 1400. So if we look at this, the time and speed, we can able to get acceleration, or we can just use this. F is equal to change in momentum over time taken. So change in momentum, that would be just be mv over t. So from here, we can have 2800 times v, that is 1400 over time, which is 1 second. So 28 times 14, that is 39.2000. Kilo is means 1,000. So if you divide this by 1,000, 1, 2, 3, 1, 2, 3, we remain with 39.20 kilonewtons, which is that. Of course, if we write into two significant figures, that will be 3900 kilonewtons. Roman 2, calculate the maximum mass that this force can lift from the ground. Ignore the air resistance. So if you look at the diagram, remember there is a weight of the rocket that is acting downward, and there's a force. So that means that the force exerted by the gases, that is acting upward should be able to balance the weight. So this F should be equal to weight, which is mg. So the force is 39.00,123 newtons. This should be equal to the mass of which can be lifted. So that will give us so the mass m. Then g is 9.8, meaning that m will be 39.00,000. Yeah, divide by 9.8. Okay, so 39 divided by 9.8. That is equal to 39, 79, 59. Into two significant figures, we will get 40, 0, 0, 0, 0. And that is kilograms. We round up into two significant figures. So just the way we have mentioned, so this formula comes in when the force that is acting upward on the rocket balances the weight. Because the moment this weight, if this weight become greater than the force, then there's no way we will expect the rocket to move upward. There will be a downward motion. So that is the maximum that can work. So they can able to carry a maximum of 400,000 kilograms. Number 3, a car has a weight of 13,000 Newton. The car is supported by 4 tires. The area of each tire is in contact with the road. Oh, sorry. The area of each tire in contact with the road is 0.016 meters squared. Roman 1, calculate the pressure on the road due to the weight of the car. So we know that pressure is given by force divided by area. So this is force per unit area. The force here is 13,000 Newton. Area, because both the car tires will be on the ground. So if each of the car tire has an area of this, then that means the total area will be 0.016 times 4. So this will give us, this will be meters squared. So that will be 13,000. 13,000 divided by, put a bracket, 0.016 times 4. That gives me 20, 31, 25 into two significant figure. That will be 20, 0, 0, 0, 0. Pressure, that is in Pascal, or it is also allowed that you give your answer into that is Newton per meter squared, just from the formula, Newton over meter squared. From the formula, that is also one of the derived units that is allowed. Okay, so once again, you can give your answer as full, or you can give normal, or you can give your answer in standard form, the way I've shown you. But then just in case you are watching this one, this particular one, this is a 200,000. 200,000 is the same as 2.0 times 10 power 4. So this is 1, 2, 3, 4, 5. Sorry, 5. 5. Good. See, I've just confirmed. That is how you confirm. Don't make assumption. Good. Now, explain in terms of particles why the air pressure in the tires increases when the car travels along the road. Of course, this is something that maybe you've observed, and if you've not, you can also confirm. When you're journeying, you will realize that the car tire become very hot. Why? And that is because of the friction. So this is due to the, so, or we can just say that the friction due to, or the friction, English. Okay, so the friction between the car tire and the road causes or causes thermal energy, which is wasted. So part of the kinetic energy is converted to thermal energy. So there's thermal energy, which in turn increases the temperature, which in turn increases the temperature of the air inside the tire of the air. So when the temperature of air increases, what does this mean? So this means that the rate of collision. So this means that the frequency of collision between air particle and the wall increases, and the wall increases. So what does this mean? This means that the force, because if it is hitting it more frequently or is hitting it more hard, so you can mention it is hitting more hard because of the speed or the frequency as increasing. That means that force increases. But the force is increasing, yet the area or the surface area of the tire is constant. So yet an area is constant. So if area is constant, this just means, of course, pressure has to increase. Of course, this is from this formula. F is equal to P over A. No, sorry. So pressure is F over A, means that if area is the same and force increases, you can able to see here that pressure has to increase. Okay. All right. Part B, a gas cylinder contains helium gas at a pressure of 2.0 times 10 power 6 Pascal. A volume of 0.026 cubic meters of the compressed gas is released from the cylinder into the balloons. Each balloon contains 0.015 cubic meters of helium at atmospheric pressure, which is 1.0 times 10 power 5 Pascal. The temperature remains constant. Calculate the maximum number of balloons that can be lifted. Okay. So if each balloon, I'm trying to adjust this. So if each balloon contains this at a pressure of this, for us to find the maximum number of balloons, it means we need to find the maximum volume of this gas, the maximum volume of this gas which is compressed in the cylinder. So if we allow the gas to be in a bigger container, then what is the maximum? So we will use Boyle's law. That is P1 V1 is equal to P2 V2. In other words, pressure is inversely proportional to the volume of an ideal gas. So that will be applicable here. Of course, we're going to assume that this gas is ideal. So P1, that is 2 times 10 power 6 times V1, 0.026. This should be equal to pressure P2. If we change that pressure, we decrease the pressure to this, we expect a higher volume. So that is 1 times 10 power 5 times V2. So from here, P2 is equal to 2 times 10 power 6 times 0.026 divided by 10 power 5. It is 1 times 10, so not much. 10 power 5 will cancel here, so we'll have here 10 power 1. 10 power 1, we will have 20. Use what is, so 20 times 0.26. We get 5.2. We get, no, 0. That's going to be 0. Be 0.52. I multiply with 0.26, that is 0.026. Okay, so we'll get this cubic meters. All right. So this is the total volume. So if each balloon contains this, that means to find the number we'll have 0.52 divided by 0.015 divided by 0.52 divided by 0. I get 34.6 recurring, 34.6 recurring. So remember, we are looking for the number. There is no way you can give the number of something in decimal place. So if we need the maximum, we'll have 34. 34. So the maximum number of balloons will be 34. So when you're looking for the number of, we need complete. The 0.6 is not complete. So we will have 34 balloons. Number 4, define the specific heat capacity. So this is the amount of thermal energy. Amount of thermal energy required to change the temperature. Required to change the temperature of a unit mass. A unit mass of any given material. Can be a substance or a material. So a unit mass of material by 1 degrees Celsius or 1 Kelvin. Change doesn't matter. All right. So, but anyway, we also know that specific capacity is given by change in energy E of so there is energy transferred over M times change in temperature. So if you know this formula here, you can write the formula, but then now you have to define the terms. You have to define that this delta E, this is energy transferred, M is the mass of the substance, then delta theta is the change in temperature. Or you can use the formula to define, you can just mention this is the amount of energy transferred per unit mass, per unit change in temperature. Wow, you're done. Get your full mark. All right, so part B, the volume of 0.0024 cubic meters of oil is heated in a pan for 7.0 minutes. The temperature of the oil increases from 20 degrees Celsius to 180. The density of the oil is 910 kilogram per cubic meters. The specific capacity of the oil is 2000 joules per kilogram per degree Celsius. What is the mass of the oil? So mass, M, I've seen the volume, I've seen density. So that means mass is given by volume times density. So 0.0024 times 910. In an exam, no matter how the calculation is easy, please use your calculator to avoid any error. So times 910, I'll get, that gives me 2.184 into two significant figures. That will be 2.2, and the unit here is kilogram. Okay, so remember about the unit. If you don't write the correct unit or you ignore, you may lose a mark. But I think if the question, like for example, this question number 4, there are different units, we need to get unit for different part of the question, you may just lose 1 mark for the whole question for the unit. But then now if there are 11 questions and there are calculations, you will lose 11 marks if you don't know the right units of place. Some of the students may say that, oh, I'll just write my value there, I don't need to write the unit. My friend, it also depends on how people are performing. If the exam is too tough, maybe they can ignore. But if the exam is easy, then yeah. So calculate the energy required to increase the temperature of the oil. The energy required, so from our formula, change in energy, so the energy transferred is given by MC, change in temperature, delta theta. So the mass we already have, that is 2.2. specific heat capacity we are given there, that is 2000. 2000. I also want to mention something here. Sometimes you are given specific heat capacity. Always check if this unit has been changed. Sometimes it is in grams. If it is in grams, that means, please, you don't need to change the unit of mass. The mass also will remain in grams. So be very, very careful. If this unit is in grams, then your mass must be in grams. If this unit is in kilogram and your mass is in grams, you must convert that mass into kilogram to avoid penalties for lack of being keen. Now 20 to 180, the temperature change there will be 160. So that is 180 minus 620, which will give us 160. So if you do that, 2.2 times 2000 times 160, that gives us 74,000. Into two significant figures, I will have 700,000 joules. Or you can leave your answer as 7.0 times 10 power 5 joules. So please don't put us. You choose which one to use. Don't put the two values or two answers in the same box here. We only want one answer. All right, calculate the power required to supply the energy calculated in part B above. So power is the rate of doing work. Power is the rate of energy transferred. So that means you must be given time here. If you don't have it, we have to calculate. So time is there, 7 minutes. So that will be 700,000 divided by 7. We have to convert into seconds. So 7 times 60. 7 cancel that. That is 1. So 100,000 divided by 60. So that is 1,666.6 recurring into two significant figures. That will be 1,700 watts. 1,700 watts. All right, so there's a blank space there. You can able to do your working out. You try a few things before you write the main. Number 5, A Roman 1, the table 5.1 shows applications of regions of electromagnetic spectrum. Complete the second column of the table with the region of the electromagnetic spectrum, each of electromagnetic spectrum used for each application. So choose from the regions in the list. We have gamma rays, infrared, microwaves, radio waves, ultraviolet. Each region may be used once, more than once, or not at all. Good. So cancer treatment, that one we have been given. Bluetooth data connection. Need a long range, so that is radio waves. Optical fibers, that is so we look at it, that is infrared from that choice, so that is infrared. Security markings, that is UV, that is ultraviolet. Sterilizing food, so that means something to kill the germs, so that is gamma rays. Wireless internet, so wireless internet, that is microwaves in a short range. All right, study the approximate speed of radio waves in air. So the approximate speed of radio waves is part of electromagnetic spectrum. That is 3.0 times 10 power 8 meters per second. The figure 5.1 shows successive crest of a wave after plane wave has passed through a gap. Okay. So on the figure 5.1, draw 3 successive crests before wave reaches the gap. So before that happens, this is diffraction, the spreading of a wave. Diffraction is the spreading of a wave if when it passes through an aperture or an opening. So remember, diffraction does not affect speed and of course wavelength. So that means that the wavelength must be the same, and then it's going to be a straight line. So I'm not able to draw a straight line from here. So I'll just try to draw, but then now you must use a line. You must use a ruler, and the ruler you're using, please, it has to be parallel. The lines we're going to draw here must be parallel to this bar here. That's what will guide you. And the wavelength, the distance between them, by the look of eye, this distance, if this wavelength, this distance should be the same here. So we need to draw 3. So I'll draw another one here. Please, my drawing is not that clear, but you understand what I'm drawing here. First, you must use a ruler while drawing this. The lines that you draw here must be parallel to this bar here. And the last thing is that this wavelength between the wavefronts must be the same to this, because diffraction does not affect speed of the wave. Wonderful. So figure 5.2 shows a much wider gap. A plane wave of the same wavelength as in B Roman 1 is incident on the gap from the left side of the barrier. So draw 3 successive crests of the wave after the wave has passed through the gap. So there is a spreading, but then now, if we look at this gap here, it was approximately equal to, the wavelength. If the size of the gap, so if the size of the gap is much greater than the wavelength of the wave, then there will be little or no diffraction. So because the gap is so wide, then it means that we expect once again the wavelength should be, so it is curved at the top. This wavelength here, by the look of the eye, this wavelength should be approximately equal to this wavelength, that because you've been told it has the same. So of course my diagram may not show it clearly. It seems to be small. It seems to be small. So there's something here that also need to take note. There's this part which is the curved part. Sorry, this part here, this part, these straight lines here. There must be straight lines which are also parallel to this bar here. And then the top or the bottom should be curved. Once you do that, you'll get your full marks. Wonderful. Question number 7. Draw the circuit symbol for a potential divider. So potential divider has 3 terminals. So this is something that you can always check from the physics textbook. So there must be part that is varying, which is able to move. So something like that, that is a potential divider. The figure 7.1 shows a circuit of a potential divider. Calculate the value of V out when the value of R is 3.0 kilowatt. So I want to show you a formula here. It may take some time, but it's good to understand. So both these are R out and R, they are in series. That means the current flowing through them is the same. So if we want to know the total current will be total voltage V, that is V in, input, over the total resistance, that is V R out plus R. So if I want V out, so V out is this current I times R out from Ohm's law. V is equal to IR. Meaning that, and my I is this. So that is V in over R out plus R times R out from here. Meaning that if I want V out, now we can able to use this. We have just proved the formula. Now, if I want V out, I just come and use this formula here direct. Oh, before I do that, V in, R out, I can just change them. So I can write here R out, and then here V out. It's the same, math is the same. It will give you the same answer. So I'll just come here and write here R out over the total value of, that is R out plus R, and this times the total voltage V in. So from this formula here, I'll just use R out as 1 over 1 plus 3 times 6. So this is a quarter times 6. That will give us 1.5. So that will be 1.5 volts. Okay. So Roman 2, the value of R is adjusted until the current in the circuit is 1.7 milliamps. Calculate the charge that flows through the circuit in 300 seconds. Calculate the charge that flows through the circuit in 300. So charge Q is IT. That means we have I is 1.7. M here is milli. Milli means 10 power minus 3 or 1 over 1,000. So times 10 power minus 3 times time, which is 300 seconds. So 300 times 1.7 times 10 power minus 3. That gives me 0.51 coulombs as the unit of charge. Let's move to the next. Part B. Electricity is transmitted at high voltage. Explain why a high voltage increases the efficiency of transmission even with the thinner wires. So remember, power is given by IV, which is equivalent to I squared R. So there are two parts here that I want to use these two equations. So for the first one, at high voltage, what does this mean? This means from here, for the same power. So at high voltage, there will be low current for the same power. So if you look at this one here, so power is IV. From here, V is equal to power divided by current, meaning that increase in voltage, there will be low current. Wonderful. So remember, current always causes heating effect, which in turn increase the resistance. So if a wire is thin already and you use high current, so you know that you will increase the resistance, and therefore thermal energy will be increased, meaning there will be more loss of power. So here that means there will be what? There will be less energy loss. So thinner wires, let's just increase, just explain thin wires. Thin wires have high resistance. That is a note that you need to mention there, that thin wires always have high resistance. But because now we are transporting power at high voltage, it means there will be less resistance. And when there's less resistance, there will be less power loss. So even thin wires can be used. But then now, what does thin wires do? So thin wires have very high resistance. That is why we need to have low current flowing through them. Number 9, part A, an experiment directs alpha particles at a very thin sheet of gold. So Roman 1, most of the alpha particles pass through the thin foil in a straight line. State the conclusion about the atoms from these observations. So let me use part of my PowerPoint that I use in my class just to explain that concept before we answer the question. So look at this. So in this experiment, what happened is that we have very thin gold leaf, then we have the alpha being derived from here. So the apparatus are set, but then now these are the observations that were made. So most of the alpha particles were seen to pass through and deflected, or they were never deviated. Some of them, so you can able to see, so few alpha particles were deflected through a small angle, but then now also very few of them also were deflected backwards. So here's how the results were explained. So number 1 is that the deflections occur because there is a force between a charged nucleus and the positively charged alpha particles. So that is why there was a deflection, these small deflections here. Then most of the alpha particles do not go near enough to the nucleus to be deflected. So they pass through, as you can able to see, like these ones here. And then backward deflections occur when alpha particles make near head-on collision with positively charged nucleus. This means that the nucleus was, is dense. So it is small but dense. Now I think we can able to, so this is what led to the discovery of the nucleus and is known as the Rutherford atomic model. So let's go back to the questions just to continue. So most of the alpha particles pass through the thin foil in a straight line. The conclusion about this is that the atom is largely made of space, or because there is a nucleus, then this nucleus must be very small. The nucleus is very small either. I think will give us a mark for that. Roman 2, some of the alpha particles are deflected through angles less than 90 degrees, and a few are deflected through angles through 180 degrees. State and explain 2 conclusions about the nuclei of atoms from this observation. So referring to the point that we've just gone there, then we can able to say that the nucleus is charged. And since we know the charge of alpha, you can actually be definite that it is positively charged. And that is because alpha particles experience a force of deflection, or we can say force of repulsion. So experience a force which deflect them. So because there's a force, so they're not moving, they're not going through the nucleus, but they're just passing near the nucleus. If that is the case, there must be a force between them, and that force, because alpha is positively charged, that must be an electrostatic force. For this case, repulsion. Another conclusion we can able to make from here is that the nucleus is very dense, even though it is small, but very dense. So how do we know about this? Because alpha particles, they hit the nucleus, but it stays. The nucleus doesn't move. That means that it's dense. That is why they're able to be hit and return to 180 degrees. Okay, part B, a source contains a radioactive isotope of strontium. This isotope decays by emission of beta particles. The half-life of this isotope is 29 years. State the change in the nucleus which occurs when beta particle is emitted. So when we're introducing this topic about radioactivity, the first thing that we always know is that, radioactivity is a process, it occurs within the nucleus of an atom. But then within the nucleus, the particles that we know are there at this level here is that we have protons and neutrons only. But then neutron has no charge, proton is positively charged. So where do we get these negatively charged beta particles, which are actually in nature, they're electrons? This always comes in terms of balance. So when an atom is radioactive, it tries to balance itself. And how does it achieve that balance? If there are too much neutrons, so neutrons is much more than the number of protons, then a neutron will convert to a proton and electron. And if that happens, now it is this electron which is emitted as beta particles. So when there's too much neutrons, so neutrons will split into proton and neutron. So because neutron is negatively charged, this is positive, the resultant charge is still 0 on either side. Roman 2, the initial mass of this isotope of strontium in the source is 25, that is micrograms. Calculate the mass of the strontium isotope that decays in 87 years. So 87, there is 29. Okay, so there is 29, half-life is 29. So we want to know the number of half-lives. The number of half-lives, that would be 87 divided by 29. 87 divided by 29, that is 3. I don't want to use calculator for that. 3 half-lives. So 3 half-lives, when you get 3 half-lives, then you have 2 options. One of the methods is a sure bet. That is the surest way, is dividing. So 25 divided by 2. 25 divided by 2, that will be 12.5. 12.5 divided by 2, that will be 6.25 divided by 2. That will be 3.125. So 3.125 is what remained. This is what remained. So remember, this is the first half-life, second half-life, third half-life. So half-life is the average time taken for it to decay by half the original value. That's why I'm dividing by 2. So if you do that, now we need to take the initial value, that is 25 minus. So 25 minus the answer, we get 20. We get 21.875 into 2 significant figures. What will have remained is 22 micrograms. There's another formula you can use to get this 3.125. You take 1/2 power n times the original value L0. So for this case, 1/2, n is the number of half-lives, which is 3, times 25. Confirm with your calculator, this should give us 3.125. I don't want. So you confirm. If it is different, you let me know. I feel that I'm sure about it. Okay, number 10. Part A, figure 10.1 represent different positions A to H of the moon as it rotates around the Earth. So So there's rays, light from the sun, we can able to see. So Roman 1, state a position of the moon where an observer on the Earth sees there's a quarter moon. So if you do so, at this particular point, this will be like new moon. If you take, let's say, light, and then you do like this, you see, this is my finger. That is how new moon behaves, because there's so much light from that side. So it looks like a blood moon. You can able to see my finger is dark, but then when I put light, see that. Yeah, like that. So part C, that will be a new moon. That means part G, this will be full moon. The only way we are going to see that is because here there is going to be light, this side will be dark. This side also will be dark. That means for part, the first number 1 is either part E or A. So you choose one, you choose one. So you can say A, or you can decide to write E. There is a position, there is this. So there is a position. We are not being asked to cite their positions. So that A and E. Okay, there is a full moon, so I think we have done that. There is a part G, position G. State the approximate time take for the moon to orbit the month. That is the Earth. That is 1 month. 1 month approximately takes 1 month. Okay. Part B, the average distance of the Earth from the Sun is 1.5 times 10 power 8 kilometers. Roman 1, calculate the average orbital speed of the Earth in kilometer per hour. Okay, so orbital speed. So if you assume it is a perfect circle, that means the distance covered there is 2 pi r. The time taken to cover one orbit, that is a time period t. So therefore, V is given by distance, which is 2 pi r over the period. So that is 2 pi times the distance, that is 1.5 times 10 power 8. We are supposed to give our answer in kilometer per hour, so I'm not changing this to meters, so it will remain that way. That is in kilometers. Time, the Earth takes about 365 days into hours, that would be 365 times 24, so that we convert it into hours. Okay, so that will give us 2 times pi times 1.5 power 8 over 365 times 24. This gives me 1075, 88, so 1075, 88.7 something. So into two significant figures, my answer will be 11,000 kilometer per hour. So 110,000, yeah, that is the speed. Yeah? Moves very fast, but when you are inside here, we don't even imagine that the Earth is moving at that speed. It's just the same way if you're in a car and all the windows are closed, you imagine you can't see anything outside. You may not able to imagine, you may not know that you are moving, especially if the car is moving on a highway where it's smooth. You can't realize that you're moving until maybe it stops. So the speed of light in a vacuum is 3.0 times 10 power 8 meters per second. Calculate the time taken for light from the sun to reach. So this is the Earth. Light is coming. So this is the orbital distance that we are using. So this is the orbital distance, 110,000. The speed we have been given. So this is very direct. So T is D over V. D is 110,000 divided by V, which is 3 times 10 power 8, but this is kilometer. No. This is speed, sorry. That is not, that is speed. We want distance, and the distance, the distance is 1.5 times 10 power 8. Yes, that is the distance. So the distance is 1.5 times 10 power 8, and it is in kilometer. So kilometer, K here is 10 power 3, because I want my answer to be in meters. Since, why am I changing that? Because the speed here is in meters per second. So they need something to cancel it with here. So I'll multiply here by 10 power 3, so that my distance is in meters. Okay, so that would be 1.5 times 10 power 11. Of course, you can just work it out directly from here. I'm just enjoying the indices here. So that is 1.5, 11 over 3, 8. That will give me exactly 500 seconds. 500 seconds. Number 11, part A, state the condition required for a protostar to become a stable star. You can always confirm this. I've already done a video, of course, using an AI, how, you know, the life scale, the stellar evolution of a star. You can check on the link above that is popping up. Maybe you do that after this. So the only condition there is that, remember, gravity pulls things inside. When they pull the nebula, and because of that friction, there is thermal energy. The thermal energy increases to be enough to support the nuclear reactions which start. When nuclear reaction starts, now there is pressure due to the thermal process, or called the thermal pressure. So when the thermal pressure, the force due to the thermal pressure balances the inward gravitational. So, you know, they're coming like this, and then there is pressure because of the heat. So this happens if the inward, or let me just say, when gravitational force of attraction, when the gravitational force of attraction balances, or is balanced because it is there, so it's not the work of gravity to balance something. So it is balanced by the force, the outward force due to the thermal pressure. At that particular point, we say that the star is stable. Define Hubble constant. So Hubble constant, H naught, is equal to V over D. If I use this formula, I have to define the terms. So H naught is the Hubble constant. This is the Hubble constant. That is H naught. And then V is the recessional speed. That is the speed. If you just say speed, this will give you 1 mark. So that's why there's 2 marks here. So then distance is the distance of galaxy away from the observer. And because you're studying from the Earth, we can just say away from the Earth. So, or from around galaxy. If you do that, you'll be able to get 2 marks. If we just say here speed without recessional or recession speed and define properly, then But then if you are not a formula guy, we can just say this is the ratio. This is the ratio. So let's just use a different mark. So you can say this is the ratio of the speed at which a galaxy is moving away from the observer to the distance between that galaxy and the observer. If you do this, for this particular one, how will you get, how do you know you have 2 marks? You must mention this. If you just say speed of the galaxy, that is a mark. So it must be the speed at which the galaxy is moving away, moving away. Oh, good. You must be keen on that. The current estimate for Hubble constant is this per second. Say the equation that give, so the time for the age of the universe is given by 1 over the Hubble constant. Calculate the estimate of the age of the universe. So that will be T of the universe is 1 over 2.2 times 10 power 18. So that is 1 over 2.2 minus 18. Sorry. So that is 4.5 times 10 power 17 seconds. And I think that marks the end of this paper. I wanted to take note of a few points that you should know as you're revising for your exam. Please, as you're revising, look at the basic things as basic as a unit. Look at the units. Don't lose a mark because of a unit, please. And prefixes. There's a whole video I've done about these ones here, so I'll just do a summary here. So prefixes. Prefix here, we are talking about kilo, milli, micro, though rarely in HCC level. We are talking about cosenti from centimeter, rarely used. You know, giga or mega, capital M, mega. So please check on the prefixes, and then if you have any challenge, check on the YouTube. We have done something about this. Unit, don't lose a mark because of unit. Don't lose a mark because of prefix. And please, 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 do not forget about the formula or the formulae in plural. You have observed, if you've gone through when we start until now, you've observed that there are some explanation, like for example, the high voltage. If you know the formula, it makes your work to be very, very easy. You can able to have a point. You have seen even from here, pressure is equal to force over area. If you know the formula, your work becomes very easy. From the definition of impulse, F times T is equal to change momentum. From there, you've seen we've derived the definition from a formula. So whatever it takes, please sit down, try to master the formula for each topic and ensure that you know how to use them and you ensure how to manipulate them. Otherwise, I want to wish you the very best. If you have any suggestion, if you feel that you are weak in any topic, let me know. I will gather the topical questions from the past paper from 2016 until now, so that I can able to work them out together. If you have any challenge, let me know in the comment. I will be able to do that work before you go for that exam. Should you have any question on this paper, should you have any suggestion, feel free to share with us in the comment section. And please be a good friend to your friend, be a good person to your friend, be honest. Share this video with your friends. All right, see you, and all the best. Don't forget to subscribe so that you don't miss any suggestion a friend of yours does here. Bye.